All right, so I'm going to talk about the fundamental theorem of calculus. This whole section is really large. And this first one, it's going to seem, I hope, really easy, but it's important that you get really good at it before you move on to the next one so that you feel really comfortable with the algebraic pickiness of it. It's going to be a little tempting to say, I can just do it on my calculator, so why bother? I will advise you against that in general, just because you're going to be more comfortable with the calculus in general if you understand the mechanisms behind it. All right, so the fundamental theorem of calculus, we're going to start with, and you see up here there's several goals. This understand the mean value theorem, that's going to be the second part. And average value, same thing, mean and average, right? Average and mean, the same thing. Second fundamental theorem of calculus will be the next video after that, and then the net change theorem. So we're going to split this up into 4 parts, and they are four huge, very important things, and they are sure to be included on one of the questions on the AP test. So it is important to spend time on this. All right, so the fundamental theorem of calculus says if a function is continuous on the closed interval from a to b, and if f, and that's important, it's continuous. That is very, very important. Continuous. I'm looking for my highlighter. Continuous on the closed interval a to b, and if f is big F is an antiderivative, right? We use big F for antiderivatives. That's a big deal. On the closed interval, then the fundamental theorem of calculus says this. If you have a definite integral from a to b, and we have a function that we're taking the antiderivative of, and big F is that antiderivative, you can actually calculate that big antiderivative at b. You can calculate that big antiderivative at a and just subtract the two, and that's the number that represents that area, whether some of it be negative and some of it be positive. That actually tells you the numeric value of that area or negative pieces, depending on what you're looking at for that function. So there's a very simple way to do that without having to do all those darn rectangles or trapezoids or some other mechanism to do it. Or if it's a parabola and you can't use geometry, well, here's a way to do it. So it can also be written this way, and this is more like the first step of how you write it. You write the antiderivative like that, and you say you're going to calculate it from a to b. Or that's for one-term items. If there's more than one term, you put the big square brackets around the whole thing. And I actually usually use that. I think it's habit from when I was in calculus, because that's the way my calculus teacher taught me. But technically you can use the one bracket like this first version if there's one term. Some people do it with just a straight line. That's usually reserved for other things though, so I encourage you to use a square bracket. That's much more commonplace notation. So why don't I have a constant of variation if I take an antiderivative? So I want you to think about it like this. If I take the antiderivative of little f, I'm supposed to get big F, okay? And if I get big F plus c, like I wrote up here, so I don't know why I rewrote it. And I do it from a to b, because really, you get a whole family of antiderivatives. Well, let's plug in that a and b like it says I can do up here. So you always put your upper limit in first. That's really important. It doesn't matter which one's the bigger number, which one's the littler number. You put in the upper limit first. Okay, so you have that, and then you do the lower limit. You substitute that in. Okay, so if you substitute that into your derivative, you get b right there, f of b plus c, and then when you do it for the second term, you get f of a plus c. But what happens when you distribute that negative? You have a plus c here and a minus c here, and they go away. So it's going to reduce to big F of b minus big F of a. It's not that the plus c wasn't there. It's that it goes away every single time. This only happens when there are limits on your antiderivative. So if there are limits on your antiderivative, meaning it's a definite integral, you're finding an actual area between two things, two values, then you can actually calculate it by doing f of b minus f of a, big F of b minus big F of a. Let me show you. So here's some examples. This first one. So forget about the limits for just a minute, let's just take the antiderivative. Remember, we add to the exponent and divide. And this one, remember, is like an x to the 0, right? X to the 0 is 1, so it's kind of there. So I'm going to write this, and no, I would never write it that way. I would just write minus 3x. And we're going to calculate that. So that's the antiderivative, right? I don't need to write the plus c, because if you want to, you can see in this first one, you write it down, plus c. You're going to write a plus c on the other side when you do your limits. And you're going to see every single time that plus c goes away. You don't need to write it as long as there's limits of integration. So what the fundamental theorem says, now that we've got an antiderivative there, you can take those two numbers and substitute them into the antiderivative. It's important that you actually take the antiderivative first. For some reason, in past years, I've had people try to do it directly into this function. No, you can't do that. That does not work. But you have to actually calculate the antiderivative. All right, so I put the 2 in to the antiderivative, which is this thing here I got, right, using the power rule for antiderivatives. And then I'm going to put in the 1. So 1 cubed to the third minus 3 times 1. Honestly, no, I don't usually write all that. But I always write, I would write just 3, and I would just write 1/3, and I would just write 8/3 probably, and I would just write 6 for this first part. So I would write 8/3 minus 6, minus 1/3 minus 3. I do always write these brackets because this negative messes with people. I have seen so many kids mess this up because they forget to distribute that negative. So please write each term that way. Now, the last step, and I wrote too big, 8/3 minus 6 minus 1/3 minus, oopsie, it's not minus 3. See, this is the stuff people mess up. That has to distribute, so it's plus 3. So I strongly encourage you not to take each part and make them all common fractions. Often they cancel right out. So I combine the common denominators first. I find sometimes it works out and I don't have to make everything fractions that way. It doesn't this time. I'm going to let you calculate that, but that comes up with negative 2/3. Now, what does that mean? It means that more of the area, when I draw it, right, this is looking like this, and I'm going from 1 to 2, more of the area is below the axis than is above the axis. That's it. That's what it means. So I'm going to switch colors, and we're going to do this guy over here. I'm going to try to write a little smaller too. All right, so if I'm doing the antiderivative, I need to make this look like, oops, you need to write your sigma. Remember, that is a sigma. It's just a sigma with n going to infinity, an infinite number of rectangles, x to the 1/2 dx. All right, so now I'm going to take the antiderivative using the power rule for x to the 1/2. I'm going to do 3x to the 3/2. Now, my little trick, instead of writing divide by 3/2, I don't like having those fractions and fractions. It really messes with me. I immediately change it to times 2/3. So I still have my fraction there, but I multiplied by the reciprocal. Instead of dividing by 3/2, I multiplied by 2/3 because I just really, I don't know, it messes with my brain. It's a personal problem, I know. So that's the antiderivative. I don't need the plus c because I'm going to put these limits of integration in. All right, so I see the 3's cancel out. I'm going to do that. Now, I personally struggle with canceling incorrectly a good chunk of time, more often than I like to admit, but by not writing those 3's down, and there are other people that can just cancel them in their head, and all the power to you. It's not for me. So I'm going to rewrite this before I go too far as 2, and remember that radical is the bottom number, so that's the square root of x to the 3rd. I like doing the 3rd power. It doesn't matter which order you do it in. I'm going to do it in, I'm going to do it second, because I noticed when I put this in, square root, now I'm going to put 4 in. You always put your upper limit in first. I noticed that I can square root 4. Now, clearly, I cube it, I get 64. I can square root that, but I find it easier to square root 4 and cube 2 than the opposite. So I'm doing it in that order because I find the math easier. You can do it the other way, though. It will work both ways. And now I'm going to put the lower limit in over here. Don't forget my cube. And you subtract it. Now, this is one where you can actually use only one bracket. It is not my habit to do so, just because I think, again, it's the way my calculus teacher taught me, so that's the way old habits die hard. I mean really old habits. All right, so this is 2 cubed minus 2, 1 cubed. So that's going to give me 16 minus 2. I got 14. Hey, got the same answers in my notes. All right, so over here, I'm going to do this next one down here. Now, it goes from 5 to 5, and I think that we already know if you're going to find the area between 5 and 5, it is going to be 0, right? That's one of our properties. But let me show you that the fundamental theorem, remember this is called the fundamental theorem for a reason. It's one of the most important, if not the most important theorem in all of integral calculus. So let's actually try and see that the fundamental theorem works with those properties that we did. Now, I did not mean to write that, so let me erase it. If I take the antiderivative of x to the third, I get x to the fourth divided by 4, right? You add 1 to the exponent and divide by that number. Now, again, you only need one square bracket, but again, old habits die hard. Okay, so now I'm going to put in 5, my upper 5. You always put the upper limit in first, and it's important which order you do it in because in subtraction it does matter. It's not important in this problem because they're both 5. But you see they're both the same, you get 0. So the fundamental theorem of calculus proves again, shows again, that that property works. Now, this last one over here, if you have more than one term, and if you have the limits of integration flip-flopped. So I get x to the third divided by 3 plus 2x to the second divided by 2 for my antiderivative. Those 2's go away. You need both square brackets here. You cannot skimp on the square brackets when there's more than one term, which is probably another reason why I just always do them, because it might be extraneous, but it's not incorrect. All right, always put the upper limit in first. It doesn't matter that the upper limit is the smaller number. You put the upper limit in first. So when you do this, you get -1 to the third. It's important that you practice safe math and substitute in parentheses, because right here, it makes a big difference. If you don't have those parentheses, you're going to get a negative number when it's actually positive. And then subtract, and then do the 5. It's important to put these parentheses. I do not suggest trying to distribute. I have watched too many students mess up their arithmetic in these over the years. Please, for the love of Pete, show a little more steps than maybe you normally would with your arithmetic. So you get -1 here because it's a cube, so -1/3, plus +1, because when you square a -1, you get a +1, minus, now you're going to get 125 thirds, and then minus, you have to distribute. Now, I don't mind if you do it here. That's a squared number, and that 5 makes that 2 look negative, but it's -25. Now, I like to combine these fractions first with a common denominator, and I combine my others. It's kind of like combining like terms, right? So I did the fraction terms, and I noticed that these divide really easy, right? The first two numbers divide by 3, it's 4, and then that's 2, so it's just -42. Minus 24, and I get -66. And so I didn't need to do everything as a fraction to be able to get this answer quite easily. All right, so now what happens if I get a little more complicated? Don't freak out just because it's trigonometry. This one, I just am going to draw a little quick picture. Actually, I'm going to draw a little bit more of this picture. That was only from pi to 4, but this is at pi over 2. Now, part of the fundamental theorem says you have to be continuous on the interval. If I had gone all the way, that's where pi over 4 is, and it says to go from 0 to pi over 4. So that's the area I'm looking for. If it had said to go all the way to pi over 2, a different story happens, but we're going to talk about that in a second. So let me put my little picture there to keep it in perspective for a minute. All right, so if I take the antiderivative of secant squared, that's one of the ones you have to memorize. Say, hey, self, what gave me a derivative of secant squared? Oh, yeah, tangent. Psst, remember? Psst. Oh, that S does not want to write. All right, so if I got secant squared, I must have started with tangent. So Tangent was my original function. That's my big F, okay, my antiderivative. You can always check if you got it right by taking the derivative of the antiderivative, and if it gives you back what you had in your integral, then you got it. All right. Now, we're going to do that from 0 to pi over 4. This is important that they're in radians. Calculus only works in radians. Actually, these formulas for our derivatives and antiderivatives only work in radians. We have to have different formulas for degrees, so just be careful that if you're using your calculator to compute things, you are in radians. Now, I would argue that you should be able to do these without your calculator. That's tangent of x. Oopsie, not x. I'm going to plug in my top value. That's pi over 4, my top limit of integration. And then I'm going to put in my lower limit of integration, and that's 0. So we're going to go to our handy-dandy unit circle. And we need pi over 4 right here, right? And we need 0. So I know that's square root of 2 over 2, square root of 2 over 2. And I know that's 1 comma 0. And tangent is sine over cosine. So for this 0, 1, right, sine is 0 over cosine is 1. That is 0 if you don't have it memorized. That's 0. If you are doing tangent at pi over 4, you do sine over cosine, which they're the same number. So root 2 over 2 divided by the same thing is root 2 over 2. You get 1. Woohoo! If you do this on your calculator, you will get 1 if you check your answer. It is important that you be able to do the mechanics of this and set up this antiderivative on your own. I could imagine that this antiderivative and use the fundamental theorem on your own. I would imagine that possibly on the AP test they would ask you to show that work rather than just get an answer with a calculator. They certainly are going to allow you to use a calculator the whole time, but I think that it is not outside of the realm of possibility that they want to see that work in this instance to demonstrate that you understand the fundamental theorem of calculus, not just how to get an answer on a calculator. I also think you might be asked to interpret this answer in context of some problem, which is what the net change theorem is that we'll talk about before we're done. Okay, that said, what if I had asked you to go to pi over 2? I alluded to that. What if I had done this number instead? The answer is you have to do more, and you have to learn about BC calculus and convergent and divergent series. And so we don't know yet if it has a limit, because you're going to have to deal with other limits, and you're going to have to come up with other calculations. The answer is sometimes it does converge, and there is a number that is an area in that problem, and sometimes there's not. It's an infinite number of area, and that is a really cool next step on what to do with integrals in a further calculus class. So something to look forward to. Now this next one, I'm going to draw a quick picture. I'm going to actually pause while I do that. So this is what I've got so far. And you know, you can plug in some values and get this, but I put in 1/2 to know that or set the whole thing equal to 0. But the thing is here, you can't take the antiderivatives of absolute values. You have to split it up into antiderivatives, you know. So if we were only going from 1/2 of this to another, it wouldn't be so bad, but we're going all the way from 0 to 2. So there's these two little triangles, and certainly you can use geometry, right, to do this. But I want to show you how to use the fundamental theorem. If you're going to use the fundamental theorem, because if this was a parabola that happened to have some absolute values involved, you would definitely need to split this up and use the fundamental theorem in antiderivatives with arithmetic, like you know. So your calculator will do this. It figures this out for you, but what is really important is that you understand that this, without an absolute value, this is a piecewise function, and that branch of the piece, or that portion of the function, has that 2x minus 1 as its equation, its numerical model. This one is negative 2x plus 1, which I think you can see from the way I drew it, but really that's the opposite of this. That's how you get that. Oops, the opposite of what's inside of the absolute value. So that's another way to do it.
So now we just have to set up two antiderivatives and basically add those two triangles together. Now, I am not arguing that you couldn't just geometrically find the area of those two triangles, but if this had been a parabola or something with an absolute value, you simply can't do that. So this is just a little bit easier way to see it. So we're going to add up the two triangles using algebraic instead of geometric methods. Now that first line from our line portion, right, from 0 to 1/2 uses this other equation. So we need to have that equation. That's the equation that we are able to take an antiderivative of. So use that one. And then we're going to add it to this other triangle, this right-hand side triangle that goes from 1/2 to 2. And we're going to use 2x minus 1 dx to calculate that. And then we actually just have to start doing the antiderivative. So remember, add 1 to the exponent, divide, and I always write it down because I make goofy errors. Remember, that's like an x to the 0, so it's like an x to the first over 1, but nobody writes that, so I'm not going to. Yes, you need both brackets here. Technically, there are people that don't write them, and it is not correct. And then you get 2x squared, divide by 2, and those are going to cancel. And yes, if you are good at that and you don't lose your coefficients or you divide them correctly, you go. I just know that I make mistakes, so I always write it so that I know that I don't make a goof. All right, so we're going to need a lot more parentheses than maybe we're used to. So I'm going to do a lot of colors and try to show you where those are. So we have to do two f of b minus f of a's, right? Two fundamental theorems of calculus. We got to do it on this antiderivative and that one. So I'm going to put in my upper limit of integration first. I need parentheses there. It's important that the negative is outside the parentheses, right? Negative is out in front of the x squared. That's like a negative 1 there. And then you square the x and multiply by negative 1. Now there's that. That whole thing, we get a different color so you can see, is f of b for the first one. Now we have to subtract f of a, which a is 0, so that's always my favorite to get. When I put in 0 to this part, that's just 0 and just 0 again, so it's really easy. It's always easy to do math with 0. I'm going to erase this little thing. It's starting to look like a pie to me. It was an arrow, a badly drawn arrow. But that's 0 right here. Okay, so that's f of b. This is f of a. So now I have my first antiderivative done. So this is the first antiderivative, this whole thing. That's how you calculate it. We have to do that arithmetic, but it's there. Plus, right? Now we're going to have f of b minus f of a for this other one, and I'm going to try to squeeze it in. Upper limit first. That's this one. Minus lower limit. Okay, 1/2 squared because there's already so many parentheses and it's positive. I'm not putting my other parentheses in. Minus 1/2, and I need a parentheses, and that finishes my f of b, f of a, my entire antiderivative here. So f of b, f of a. Right now it's just arithmetic. That's negative 1/4 plus 1/2 minus 0. I'm not writing because why? Minus 2 minus 1/4 because 1/2 squared is 1/4. And then this is distributed. That looks like a 3 for my parentheses, but remember that denominator's a 2. So it's going to be plus 1/2. All right, I see already that I can combine 1/2 and 1/2 is 1. That's 5. Minus 2 is 3. So I have 3. And the 1/4s when I put it together are minus 2/4 or 1/2. So I get 2.5. Now you could have done that other ways, but I like to just combine what I can, kind of like combining like terms with fractions. That's really what you're doing. Common denominators first, and if I have to afterwards make everything common denominators, I do. All right, it's getting long. The video is getting long, so I'm going to do the next part in another video, separate video. And there's 2 slides to finish up, and they're a little bit more complicated, so I'll do that in another video. So try to practice some of these. It'll make the next video a little bit easier, so maybe practice some of the CUDA sheet first. Watch the next video, and you should be really golden on the first fundamental theorem of calculus.